try one note. See what crash is left. We come up with a sodium hydroxide concentration of this is a sodium hydroxide initial, where we started off at the beginning of step 1, minus the amount we consumed in step 1, minus the amount we consumed in step 2. And so I just multiplied this by 2. Is this where we stopped? Okay. So what we're going to do is we're going to do the same assumption. We're going to just assume that the weak base doesn't contribute significantly. We could do a step 3 to this. That is, we can see oxalate, which would be something like this. Oxalate itself is a pretty decent base, because hydrogen oxalate ion isn't such a strong acid. So this would be a potential step 3. The potential step 3 would be oxalate, which is a dibasic base, can hydrolyze water to produce hydrogen oxalate and hydroxide. But due to the common ion effect, the common ion effect would have this is our initial sodium hydroxide here. Due to the common ion effect, and due to the fact that oxalate is a weak base, but it's a fairly strong weak base. That's the only problem. We're going to assume that we won't get too much additional hydroxide from this step. And so common ion will reduce the amount of hydroxide produced in this step, and therefore the common ion effect means we're going to assume that the additional hydroxide is not significant. That would be generated in this step. In other words, this is a mixture of strong base, weak base. And as long as the concentration of the strong base is greater than, let's say, 10 to the minus 6, then we're good. And so the strong base here is going to be greater than probably 10 to the minus 6. If it gets down low, like 10 to the minus 7, 10 to the minus 8, then we have to worry that the weak base would be a contributor. But let's see what the concentration comes out to here. Actually, we know what the concentration comes out to because we want the pH, and so we're going to skip this step here and go back to here. I'm going to stop at step 2. We have an idea of what the concentration is because we're stopping at a pH 11.00. This is quite basic. There's a lot of hydroxide here, which means the pOH is what? 3.00, which means the hydroxide concentration is 1.0 times 10 to the minus 3. Which is a lot of hydroxide. And so what we'll do here is we'll just plug this into the equation. That hydroxide we're going to assume stops at step 2. So this is equal to the sodium hydroxide total. The total sodium hydroxide is, or actually it's not equal to the sodium hydroxide total. It's equal to the hydroxide total. And the total hydroxide is equal to the excess sodium hydroxide plus the hydroxide generated from Kb, the weak base, plus hydroxide that's generated from water. So from Kw. But as I mentioned, we're going to ignore these contributions here because we expect these to be negligible. And therefore, we're just going to assume that it's the same as the excess hydroxide there. If it's the same as the excess hydroxide here, then we have two unknowns. The excess sodium hydroxide left over at the end of step 2 is equal to the sodium hydroxide initial minus the amount neutralized in step 2 plus the amount neutralized in step 1, which is equal to the concentration of oxalic acid initial. We have two unknowns, so what we're going to do is we're going to do substitution next. So the sodium hydroxide initial, that was, we don't know how much we had in there, but it's x over 20 plus x times 0.1. Okay, minus 2 times the oxalic acid initial. The oxalic acid initial was a 20 over 20 plus x times 0.1. Right, so that was my mistake earlier. And so what I'm going to do is I'm just going to factor out the 0.1. And this is going to equal 1.0 times 10 to the minus 3. So factor out the 0.1 and divide both sides by 0.1, which means that's going to be 10 to the, divided by 10 to the minus 1, that's going to give us 10 to the positive 1. And so we're going to get x over 20 plus x minus 20 over 20 plus x is equal to 1.0 times 10 to the minus 3 divided by 0.1, which is going to equal 1.0 times 10 to the minus 2. And then we're going to get x minus 20 over 20 plus x is equal to 1.0 times 10 to the minus 2, which is just equal to 0.01. And so I'm going to just go through the steps of solving this. X minus 20 is equal to 0.01 times 20. It should give us 2. And then is that right? No. It gives us 0.2, right? Plus 0.01x. So this comes out to, what I'm going to do is I'm going to subtract 0.01 from both sides. So if I do that, I'm going to have 0.99x, and then add 20 to both sides. This is going to equal 20.2. And therefore, x is equal to 20.2 divided by 0.99, which is equal to, let's see what that's equal to. I might have screwed up the math again. This is equal to 20.4. Did I miss something? I think I missed something. No, I didn't multiply by 2. 20.4 is impossible. Why is it impossible? Number. Because look at the titration curve. 20.4, is it after the first equivalence point or after the second equivalence point? It's right after the first equivalence point, which would be in buffer region 2. We should be after the second equivalence point. And so when I was looking at this number, I was thinking, oh, I made another mistake, unfortunately. So where was my mistake? Here, I forgot to multiply this by 2. And so what that means is this is not 20 here. This should be 40. 40 milliliters is at the second equivalence point, so it should be a little bit past the second equivalence point. And so this should have been 40 here. This should have been 40 here. And this should be 40.2, not 20.2. Okay, now this looks more reasonable. So 40.2 divided by 0.99. It's 40.60. Okay, now we're past the second equivalence point, and it comes out to 40.60 milliliters. But this, of course, is reasonable because we expect to be past the second equivalence point, not the first equivalence point. But even though it looks reasonable, I'll still want to double check it. Now, how do I double check my answer? Well, we're just going to plug it in and do the problem over again with plus 40.60 milliliters of sodium hydroxide. So what we'll have is I'll have our 20.00 milliliters of oxalic acid, and we're going to titrate it plus 40.60 milliliters. That's going to give me a total volume of 60. 60.60 milliliters. All right, then we'll figure out the dilution factors. For the acid, we had a 20 to 60.6 dilution of 0.1. This is 3 sig figs. So I'll just keep track of the sig figs here in my head. I probably should write it out so I don't forget. But this is how I'd punch it in my calculator. And I'm going to get 0.03300. I'll carry one extra digit here, molar, just to show. And then for my sodium hydroxide, what is the dilution factor here? The sodium hydroxide is going to be 40.60 milliliters originally, is going to be diluted to 60.60. I'll keep all the sig figs here, times 0.100 molar. But in my calculator, I'm not going to punch in those. So I'm just going to punch in 40.6 divided by 60.6 times 0.1. And this gives me 0.06699 molar. Here I'm carrying an extra digit. Normally if I carry extra digits, you know, to mentally keep track of the extra digits, I always subscript those so that I make sure I conform to the sig fig rules here. but I don't want to round yet because I need to round at the very end. And so when you have extended calculations like this, I always carry at least one digit, but not too many more, otherwise it's too much calculator punching. All right, now we'll go to step 1, which is going to be the oxalic acid plus the sodium hydroxide. This is going to yield sodium hydrogen oxalate plus water. You know, on tests, I don't know, it's probably due to not having enough practice, but on tests, you know, people say, well, oxalic acid is diprotic acid. Shouldn't you be adding 2 sodium hydroxides to this? And so I see ice tables with 2 sodium hydroxides. Is that right? No, that's wrong, because we always neutralize just 1 proton at a time. But there is always going to be, every semester, somebody who's going to write 2, which is fine for writing like Chem 1A, you know, metathesis reactions or that kind of stuff is fine. But in Chem 1B, we don't do that. And so the limiting reagent here is going to be the oxalic acid here. I'm going to go 3,300 to just carry 1 extra digit. And the sodium hydroxide is going to be the excess reagent. And so I'll go 6699 here. And then we're going to lose all our limiting reagent. This is going to go to 0. And then this is going to be minus 0.03300 molar. And so this is going to give me a remainder of 0.3399 molar here. And then over here we're going to plus 0.03300 molar here, and water blank. Okay, this goes to completion. Strong always goes to completion. You just need 1 strong species in there, and we don't do an equilibrium. We don't calculate X. All right, and then it is a diprotic acid, so we're going to lose the next proton in the next step with an additional sodium hydroxide. So what this is saying is, this is saying that the first hydrogen is the most acidic, and that has to be completely reacted before we move on to the second hydrogen. And that's going to give us sodium oxalate plus water here. Okay. And so the amount of sodium hydrogen oxalate is amphoteric. Amphoteric species can act either as an acid or base, but in this case, even though sodium hydrogen oxalate is an amphoteric, it's not going to act as a base. Why? Because sodium hydroxide is a much more powerful base. And so sodium hydroxide will assume the role of the base, therefore sodium hydrogen oxalate has to assume the role of the acid, even though it could go either way. And then the sodium hydroxide is in slight excess. We can see here just 0.03399, just a little bit excess here. And then we're going to lose all our limiting reagent, and then we'll go minus 0.03300 molar, and that's going to leave us with 0.00099 molar here. We're also going to generate some weak base. In fact, we're generating even more weak base than strong base. But because the strong bases, remember, strong bases are hydrolyzed 100%, weak bases is just partially hydrolyzed. So even though we have a higher concentration of weak base, the amount of hydroxide we have is going to be less, a lot less. And so, especially with the common ion effect. So we're going to stop here, and we're going to calculate the pOH. The pOH is going to be the negative log of the hydroxide, which is going to be 0.00099. So what does that come out to? 0.00099 log. It comes out to 3.004, which means the pH is going to be 14 minus that, which is going to be 10.995. How many sig figs is this, our pH here? Right now, I count 3 sig figs, which is too many. Everything after the decimal is significant. Everything preceding the decimal is not significant. And so I need to change this to 2 sig figs for my final answer. So my final answer, I'm going to round that up. I'm going to round it up to 11.00. So this is a good check here because I'm just going to go full loop. It doesn't always work when you do the full loop because sometimes it's like an error where you make one error and then that error is systematically reproduced and gets you the correct answer, but there's an inherent error in there. So it doesn't always work, but in this case it works, you know, as a double check. Sometimes it's difficult to double check. So if you can't double check something like this, you know, so for example, I know I could double check it like this. If I couldn't double check it like this, then I'd be much more careful with my algebra up here, you know, and I'd double check my algebra to make sure I didn't make a simple mistake like multiplying, dividing, adding, or subtracting, that kind of stuff. It's very common mistakes in these calculations. Okay, so that's titrations. What I want to talk about next are indicators. And so let me talk about that. We have two different things. We have the endpoint and the equivalence point. And what's the difference between the titration endpoint versus the titration equivalence point? Really, we just want to get to the titration equivalence point. Then at the first equivalence point, second equivalence point, etc., you know we have just the right amount of base to neutralize the acid, correct? Just the right amount. Sometimes people put the acid in the burette and the base in the flask. And so our titration curve is inverted. You know, we start off high and then go low. But essentially it's the same thing. However, it's invisible. Can you visually see when you hit the equivalence point if you didn't put an indicator in there? No. Visually you can't see. But the problem with indicators is they don't change color at the exact spot you want them to. They either change color a little bit before or a little bit after. This consecutive means stepwise for me. Actually, I'm in the wrong chapter. Sorry, no wonder. They switched around chapters from the previous edition. So they inserted a chapter here. Let's take a look at indicators. Here. And there's a diagram here that shows you where the color changes. So I guess they didn't have enough ink. So for example, here thymol blue stays red, and you can't really tell the shade of red until you hit here, and then it's going to transition to yellow. But in the transition region here, it's orange. So if we use thymol blue, it'd start off with red in the acid and eventually start to turn orange. And then as you go past orange, it stays yellow all the way out here. So thymol blue is pretty much not used for anything in the red region, not used for anything in the red-yellow region. It's only used for the orange region here. And the pH at which it starts to turn orange is what? Let's see what the pH is here. Around 1 to 2. So So let's say around pH 2, we start to see the orange color. Is that going to be very effective in our titration? No. In our titration, pH 2 is in the buffer 1 region. So we'll see that. So this indicator would start to change color well before we hit the equivalence point. Where was our equivalence point? 8 point. Oh, actually, what was our first equivalence point? Actually, I didn't calculate it, did I? Or did I calculate it? I didn't calculate it. Did anybody calculate it? The first equivalence point in our titration was invisible. You didn't even see it. The reason is we didn't have an indicator in there. I suppose we could have put an indicator in there. But thymol blue wouldn't be worth it because it would change color down here. We need something to change color at our first equivalence point. The pH at the first equivalence point here is equal to the pKa of our acid, which is oxalic acid, plus the pKa of what? Actually, it's not the pKa of the oxalic acid. What was it? Yeah, this is what we're left with in step 2 is a amphoteric salt. The problem with amphoteric salt and water is that the amphoteric salt can behave in both ways. The amphoteric salt with water can either act as a base or an acid. In fact, it acts as both. So there's going to be a Ka and a Kb. However, when we have an amphoteric salt with sodium hydroxide, the sodium hydroxide is a dominant base. Therefore, the amphoteric salt can only act as an acid. But with water, we can go either way. Therefore, it's simultaneous. And we come up with this equation. It's going to be the pKa of the amphoteric, which is hydrogen oxalate ion, plus the pKa of its conjugate acid. What's the conjugate acid of hydrogen oxalate? Oxalic acid, divided by 2. So let's go ahead and get the pKa's for these. Can someone remind me, what was the Ka? I think it was 5.9 for hydrogen oxalate. So it's 5.9 times 10 to the minus 5, was it? Did somebody write it down? Yeah, my Word crashed yesterday and I lost most of my notes. I only have 1 page of notes from yesterday. All right. I don't have the rooms chart here. I'm just going to use the book's value. So I could either go back to chapter 17 or I could end appendix D. I don't know which one's going to be faster. Appendix D, I wish they broke it into different sections. So they group all the tables together. (5.3 times 10 to the minus 5). As I recall, the book in the classroom chart was 5.9 times 10 to the minus 5. But it's okay. 5.3 times 10 to the minus 5. Be aware of that. It's going to be different than what I had used before. But I'm not positive because my memory's bad, so we'll just go with this. 5.3 times 10 to the minus 5 from the text. Okay, so what we want is we want the pKa for that, the power function. So this is going to be the negative log of 5.3 times 10 to the minus 5. Let's see what that comes out to. 5.3 times 10 to the minus 5 log 4.275. I'm only allowed 2 sig figs, but as I said before, I'm going to carry one extra, 4.27, and the one extra I carry is going to be subscripted so I can keep mental track easier. I don't have to remember it. Okay, then we need the Ka for oxalic acid. The Ka for oxalic acid, H2C2O4. I'm just going to use the textbook's Ka value, which is 5.4 times 10 to the minus 2. 5.4 times 10 to the minus 2. There are a lot of tables that will give you the pKa value. And so I'll just take the negative log. I'm not going to write the equation here, but 5.4 times 10 to the minus 2, which is fairly strong. You know, 10 to the minus 2 is on the strong end of the weak spectrum. Take the log of that. 1.267. I think I forgot the number I got in class, but it's different, right? It was like 1.23, wasn't it? This is going to be 1.27. So it does matter what chart you get your K values from, but we'll just go with this here, since I don't remember the value for oxalic acid. I used it all. And therefore, the pH is going to be, it's a pretty simple equation, 4.275 plus 1.267 divided by 2. So 2.77. 1. So the pH is 2.77. If I wanted to see the first equivalence point, then I need an indicator. You know, this is the equivalence point. I need an indicator that changes color at 2.77. Let's see if I can find an indicator that changes color at 2.77. So that's almost 3, 2 3/4. So we'll drop down here. I'm going to not move my mouse horizontally. Do I have an indicator that changes color at 2.77? That's where my mouse is. Do you see it? I don't. Not in this list. Maybe I'm going to have to look in, you know, because this is not a comprehensive list. Maybe I'm going to have to look in a different list. But I don't. So if I used any of these indicators, what's going to happen, maybe this is close here, and this is close here. And so thymol blue and bromphenol blue are kind of close. But they're off, you know. This is hitting the yellow region. So maybe when it transitioned from orange to yellow, we stopped there. However, it still might be okay. And why might it be okay? It still might be okay because it depends on how steep the rise is there. The first equivalence point, you don't have much flexibility here. Because let's say, where does that indicator change color? That indicator changes color at, let's try to get it more precise here. Oops. It's not. What happened to my, here it is. This indicator changes color at about 1.9. Around 2, just slightly less than 2. And this indicator changes color, bromethymol blue, around 3.7. And so around 2 and around 3.7. It depends on where we are. So, for example, if we're here, is this around 2? If this is around 2, then the error isn't going to be so huge. This way. This is the error here. Because that's a big change in pH here, maybe. Or 3.7, maybe that's here, catches the top shoulder here. So those indicators might give you an indication of where it is. And it depends on how steep that first rise is. If that first rise is quite steep, then the error is not going to be so significant. And so we can use different indicators for things that it might not be perfect, change perfectly at the equivalence point, but it's close enough that it leads to a very small error. All right, so let's take a look at some of these other indicators. The most used indicator on this list is which one? It's probably this one. Phenolphthalein stays colorless from pH less than 0, negative pH, all the way up to about 8 to 9, and then 9. Here it's so faint, and so here we're titrating this to about pH 9 here. This is when the faint pink becomes readily apparent, or maybe a little bit before. But we use phenolphthalein for all titrations. We use it for strong acid, strong base titrations. Strong acid, strong base produce neutral salts. Neutral salts have an equivalence point of pH 7. If we're titrating to an equivalence point of pH 7, our end point is pH 9. Is that a huge error? So let's take a look. At this, see if I can get it. It turns out it's not a huge error. I need to show you the titration curve itself. You can see that. What happened to my titration curves? Oh, here it is. So this is the equivalence point of our titration, but the end point of our titration is here. This is normally where we stop in a Chem 1A style titration. But you see the error? There's a huge error in pH. But did that huge error in pH result in a huge error in volume? No, in terms of volume, that's way less than a drop. And so that's minimal. So we could have used phenolphthalein. However, if we use alizarin yellow is a huge change in pH and a significant change in volume, because we would have stopped right here. If we stopped right here, that volume was way off. And so phenolphthalein works fine. This is perfect. This one's called bromethymol blue. Bromethymol blue has an endpoint of pH 7. Because at pH 7 we have green. And so this is perfect. So why don't we use bromethymol blue? The reason we don't use bromethymol blue is because it's harder to detect the subtle color change. You know, it's going from yellow to green to blue, and so it's hard to detect that subtle color change consistently. Whereas phenolphthalein, it's easier because we're going from colorless to color, so we're just looking for any color, not a particular shade. This is a particular shade of green that we're looking for, and it's difficult. And so people don't, even though the endpoint and the equivalence point would match perfectly for strong base, strong acid titration, we don't use it. A methyl red is fine too. We could use methyl red, it turns orange here, but again, what shade of orange do you stop at? It's too difficult. Bromophenol blue would work. However, thymol blue is way off. Thymol blue changes to orange here or yellow-orange here, and so we'd be way off. This is strong acid, strong base. Now, for weak acid, it more closely matches. I think they don't show the weak acid one here, but we calculated a equivalence point of pH of about 8.7, so phenolphthalein's perfect, you know, for us, or close to it. And so I want to talk about indicators next, and then another way of making buffers, and then I'll stop. That's the end of this chapter. So indicators are weak acids usually. Weak acid, weak base. And these are conjugates. If we have a weak acid, weak base combination that are conjugates, what do we call that? What type of mixture is that? We call this a buffer mixture, and since they're conjugates, we call it a Henderson-Hasselbalch buffer. And so this is an HH buffer. I got to figure out how to make this little cursor dot bigger in OneNote. I can barely see it. But there's one more criteria. The weak acid has to be a different color than the weak base. So there's got to be an acid color and there's got to be a base color. So if we look at the Henderson-Hasselbalch equation, which is this, that the pH is equal to the pKa plus the log of base concentration over acid concentration. There are three important points here that we have in terms of pH. We have pH is equal to pKa minus 1. If pH is equal to pKa minus 1, that's pKa plus a log of a ratio of 1 to 10. So that's 1 part acid, 10 parts base. I'm sorry? Oh, oops. No. Why is the one the acid that's wrong? Thanks. 1 part base, 10 parts acid. Sorry. So in this case, acid color dominates. So if the pH is less than or equal to pKa minus 1, the acid color dominates because the lower goes. So for example, if we go to pKa minus 2, that's a 1 to 100. pKa minus 3 is 1 to 1,000. 1 part base, 1,000 parts acid. So the acid color is going to dominate here. If we're in a range of this, if we're in between, let's say we have our pH is in between pKa minus 1, so we're greater than pKa minus 1, but we're less than pKa plus 1, then we have a mix of colors. So for example, if we're at a pH equal to the pH equal to pKa, that means we have a 50-50 mix. Because this is pH is equal to pKa, at the half equivalence point, let's say, that we saw in the titration, but what it means is that we have a 1-to-1 mix of acid and base. So that means pH is equal to pKa plus the log of 1 part acid to 1 part base. So this is a 50-50 mix. So as long as we're close to a 50-50 mix, then we're going to get a mixed color. So for phenolphthalein, the acid color is colorless. The base color is red, and so our 50-50 mix is going to come out pink. All right, so the next one is if we have our pH greater than or equal to, let's just go pH is equal to pKa plus 1. That means we have a pKa plus log of 10 to 1. 10 parts base, 1 part acid. And so the base color dominates when the pH is greater than or equal to pKa plus 1. So when we go to the indicators, this is what we'll see here on the indicator chart. This is what they're showing here. They're showing in the center is pKa, and then we go pKa minus 1, that's the acid color, dominates. And then we start from pKa plus 1, the base color dominates here. It's just going to stay violet. However, in this range between pKa minus 1 and pKa plus 1, we have a mixed color here. And so right in the center, we have a 50-50 mix. And when we get that 50-50 mix, it depends on, what's more dominant. Is the base the stronger, or is the acid the stronger? For these indicators, the acid is stronger than the conjugate base. For those indicators up there, the base is stronger than the conjugate acid. And so that's why the pH is so high for these and the pH so low for these. Here, for something like bromethymol green, the acid and base are comparable in strength. All right, so here's the chart here showing which color is dominant. All right, the last thing is there are different ways of making buffers, and the different ways of making buffers is we could use a titration. So here, if we titrate the strong acid and strong base, is this a buffer region here? You'd think this is the buffer region, but it's a strong acid with a strong base. A strong acid with a strong base makes a neutral salt. So this only has acid. There's no base mixed in here. And so it turns out this is not a buffer. When we have strong acid, strong base, you can't make a buffer. But we can use a strong acid or a strong base to make a buffer by titrating. So here, here's a base. We're starting off with the base in the flask and adding acid in the burette. And so this is inverted. But this is a buffer region here. This would be like ammonia being titrated with hydrochloric acid. You know, ammonia is going to get converted to ammonium. Ammonia is a much stronger base than ammonium is an acid, therefore it's kind of high in pH here. This would be a buffer. However, this region is not a buffer because this is just excess strong acid. So this would be a mixture of strong acid, weak acid. A strong acid, weak acid mixture is not a buffer. This is the buffer region here. This would be like acetic acids and sodium acetate. So this would be acetic acid acetate buffer region. And here at the half equivalence point, the pH is equal to pKa. Past this would be just excess strong base, weak base mixture. And that's not a buffer solution there. This is phosphoric acid. With phosphoric acid, here, this first equivalence point is pretty clear. We don't start too low. Oxalic acid was a strange one. Start low. So this first equivalence point we could see, and they're choosing the indicator methyl orange, which is fine. The methyl orange seems to hit it perfectly. You know, it changes to a light orange here, right about where the equivalence point is. And then this is pretty close. You know, this hits it a little bit too early. Phenolphthalein, but the error associated with hitting it just slightly early is just minimal, less than a drop error here. And so the end point is a little bit too early. The end point here is about perfect. Well, it's still slightly early, but not much. So the first equivalence point's easily visible. There aren't significant errors here. So this is buffer region 1. And then we pass the first equivalence point. This is buffer region 2. It's pretty steep. You'd expect buffer region 2 to be fairly flat. So I think it's flatter than what's shown here. And then we're up here, and this should be buffer region 3. And the third equivalence point should be, here's the first, the second. The third equivalence point should be, how many blocks is that? 4, 4, another 4. The third equivalence point should be right here. Do you see it? We don't see it because the only way you could see that is if you made it a lot more concentrated. This is not concentrated enough. This is 0.1. And so we can't get the pH high enough using 0.1 molar sodium hydroxide. Maybe if we use 6 molar sodium hydroxide, then we can get the pH high enough that we'd see the third equivalence point. So the third equivalence point is invisible in this titration. So if you look here, I see here buffer region number 2 is here. And what's the optimum pH of buffer region number 2? It looks like the optimum pH. What was the optimum pH of a buffer again? The optimum pH is where we have a 50-50 mix of acid to base. When we have a 50-50 mix of acid and base, what's the log of 50 over 50? This would be the log of 1, which is 0, and therefore the pH is equal to the pKa. So the optimum pH of this buffer is right here, which is about pH 7. However, the optimum pH for this buffer is much lower because the acid component is much stronger than the base component. And so the optimum pH here is about a little over 2. Do you see that? What's the buffer range? You know, we don't want the buffer to become too lopsided, so we have a buffer range. What's the buffer range? It should be between we don't want it to go more than a 10 to 1 way or the other. And so the buffer range is what? pKa plus or minus 1. And so what that means is we won't make too lopsided the buffer as long as we keep the pH within plus or minus 1. And so it's about 7. So between the 6 and 8, this would be the buffer range here. Do you see that? So we can make a decent buffer here. You know, if we go beyond that, it becomes too lopsided in acid over here and too lopsided in base over here. Does that make sense? Okay. And the same thing, the buffer range here would be plus or minus 1. And so there are different ways we can make a buffer. Let's say I wanted to make a buffer pH 7. Okay, how would I do that? I want to make a buffer of pH 7.00. So if I have a buffer of pH 7.00, what can I use to make this buffer? Well, I would look for buffers with an acid component that has a pKa around 7.00. So we want an acid with pKa 7.00. If I had an acid with a pKa of 7.00, then it's simple. I mix the acid and base components in a 50-50 mix. But the problem is do I have something with a pKa of 7.00? Well, a pKa of 7.00 is a Ka of 1.0 times 10 to the minus 7. So I'm looking for something as close to a Ka of 1.0 times 10 to the minus 7. So let's take a look at our choices here and see if I have an acid that has a Ka of 1.0 times 10 to the minus 7. So 10 to the minus 5, 10 to the minus 5, 10. Oh, here I got it. This is perfect. Do you see that? So if I made a 50-50 mix, this would be the acid component. And what would be the base? What's the conjugate base of dihydrogen arsenate? Would be monohydrogen arsenate. That would be the conjugate base. So if I made a 50-50 mix, then I'm spot on, 7.00. But there's a problem with using hydrogen arsenate, and that problem is it's quite toxic. So to make a buffer that's not terribly poisonous, let's skip this here and see if there's something less toxic. 5, 3, 5, 7. This is carbonic. Is somewhat close. But there's a problem with carbonic. How do we make carbonic acid? To make carbonic acid, you have to bubble CO2 in water. Is it easy to control how much CO2? No, that's extremely difficult. Even though the carbonic acid bicarbonate buffer is used in your blood to help maintain pH. For us, it's too difficult. We'll skip that. This is close. Monohydrogen citrate. This is from citric acid, and citrate's the ion. Citric acid is the acid here. So triprotic acid. So if we use monohydrogen citrate and citrate ion as the acid-base component, then that's fairly close, 10 to the minus 7. It's off a little bit, but we can adjust it. We just add a little bit more base than acid. A little bit more base than acid will bring the pH down. So we just alter the ratio a little bit. And so this is close. However, there's a problem with citric acid. Do you know what the problem with citric acid is? It's electron rich. Citric acid is prone to oxidation. So you might make a nice buffer. It might smell nice. It might even taste pretty good. But it's not going to last very long because it's going to go bad. It's going to spoil. So we don't want to use citrate. Citric acid. It's fairly electron rich. And it's a good reducing agent. 4, 5. So I'm looking anything. I'm looking for 10 to the minus 6, 10 to the minus 7, 10 to the minus 8. Anything close to that. Ooh, this looks perfect. Here. Hydrosulfuric acid looks perfect. A 50-50 mix of hydrosulfuric acid with hydrogen sulfide ion would make a pH 7.00 buffer. But what's the problem with using hydrogen sulfide? One, nobody would want to use this because it smells like, you know what hydrogen sulfide smells like? It smells like rotten eggs. In fact, that's what rotten eggs give off. Rotten eggs give off hydrogen sulfide. And so not only that, hydrogen sulfide is toxic at the part per billion level. Number one, it's not good because of the smell. Number two, it's not good because of toxicity. And number three, it's not very soluble. The max hydrogen sulfide you can get in water is 0.1 molar. So skip that. Hypochlorous acid would work. We use hypochlorous acid. That's not terribly far off, I think. You know, the closer we can get to 10 times 10 to the minus 8. 10 times 10 to the minus 8 is 1 times 10 to the minus 7. So the closer we can get to 10 times 10 to the minus 8, we're close. But hypochlorous acid is bleach. And that's kind of nasty to work with, so we're going to skip that. Let's see, let's shrink this down a little bit. Hyponitrous acid, don't want to use that. That's very close. We need 10 times 10 minus 8. That gives us 1 times 10 minus 7. Very close. But hyponitrous acid is toxic as well. You know, a lot of these oxides of nitrogen are quite toxic. It's way off, way off. 2 times 10 to the minus 6. We want 0.1 times 10 to the minus 6. 0.1 times 10 to the minus 6 is 1 times 10 to the minus 7. So this is not terribly far off. Malonic acid. The problem with some of these organic acids like this are they're prone to oxidation. Because the hydrocarbon part of the acid wants to burn. And so malonic acid we're not going to use, although malonic acid is used in a lot of chemistry, and it's not terribly toxic. They use it in cosmetics and other stuff, malonic acid. Oh, this is very close. Oh, this is the buffer we were just looking at, dihydrogen phosphate. This is buffer region 2 for the phosphoric acid titration curve. This is 2.1 times 10 to the minus 7, so this is very close. And phosphate is no problem here in terms of toxicity compared to other things. This is very close too. Pyrophosphoric acid, though. I'm not going to use that. That's not as common. Phosphoric acid is cheap. And so I think that looks like the best out of these. Succinic acid is pretty good too. That might work here. Not succinic acid, but hydrogen succinate. This is getting close to 0.1 times 10 to the minus 6. Thiophenol. We avoid thiols. Thiols smell bad in general. These sulfur-containing compounds. Okay, or we could go to the bases. So if we want a Ka of 10 to the minus 7, we want a Kb of 10 to the minus 7. And so we could look at the base and its conjugate acid and use the same Henderson-Hulse box. So anything around 10 to the minus 7 Kb would be about 10 to the minus 7 Ka. And so we could look here. But a lot of these are means, you know. They're going to smell like ammonia. There's codeine. Yeah, a lot of these amines smell bad. So we just avoid those. And some of them fume. The ammonia, have you smelled the concentrated ammonia? It's pretty nasty. You'd have to use it in the hood. All right, so it looks like the best choice we have is dihydrogen phosphate, 6.3 times 10 to the minus 8. And so we're going to go here and take a look. So first is acid-base selection. We just went through that, and so we're going to pick the dihydrogen phosphate, which has a Ka of 6.3 times 10 to the minus 8. Or no, I chose the wrong one. Sorry. Let me redo that. 7.2 times 10 to the minus 7, I think it was, or something like that. Let me check that again. Oh no, that was right. 6.3 times 10 to the minus 8, which is close to 10 times 10 to the minus 7, which is close. So let's see, 6.3 times 10 to the minus 8, log of that gives us 7.200. So we just need to add a little bit more extra acid. A little bit of extra acid will bring that down. So let's go ahead, and the first thing we're going to calculate is the ratio. So we want a pH of 7.00. This is our desired pH. Our pKa is 7.200 plus the log of the base to acid ratio. And so we're going to solve for the base to acid ratio here. And so the base to acid ratio is going to be equal to the anti-log of minus 0.20. So let's do that. Negative 0.20. 0.6309. So what we need to do is we need to put in 0.6309 parts of base. The base in this case would be monohydrogen phosphate for every 1 part acid, which is the dihydrogen phosphate. The base and the acid must be conjugates, so be careful. These are conjugate pairs. All right, and so the more concentrated, the higher the capacity. The less concentrated, the lower the capacity. And so, for example, I could try to make it 10 molar and 6.3 molar. You know, I don't know if I can get 10 molar dihydrogen phosphate, but we could try 6.309 molar monohydrogen phosphate to 10 molar dihydrogen phosphate. This would be high capacity buffer versus a low capacity buffer would be like 0.0006309 to 0.001. Is that right? No. Yeah, that's right. This would be low capacity. The difference is its resistance to pH changes. This has high capacity to neutralize things that you might add. And so this is going to make a pH 7 buffer. And so let's compare a buffered versus unbuffered, and then I'll stop here. Let's do unbuffered first. I'm going to add 1 drop of 6 molar HCl to 250 milliliters of water. And so what this is going to give me is it's going to give me 250.05 milliliters of mix. And then I have to do solution dilution. And so my new concentration of HCl is going to be a 0.05, which we're going to call 1 drop, over 250.05 dilution of 6 molar. And so a 0.05 divided by 250.05 times 6 means my new concentration of HCl is quite small. It's 0.001199 molar. Am I going to worry about Kw at this? What is this? This is 10 to the minus 3. Do you worry about Kw at 10 to the minus 3? Even though this seems very small, I'm not going to worry about Kw at all. And therefore, the pH is going to be the negative log of that. So take 2.92. 0. So what happened was I went from pH 7, if this were pure water, down to pH 2.92. Would you call that a significant change in pH? Yeah, with just one drop of 6 molar HCl, that was a significant change in pH. Okay, we're going to just take a medium capacity buffer, not the super high one. What I'm going to do is I'm going to add 1 drop of 6 molar HCl to 250 milliliters of pH 7 buffer. But it depends on the capacity of the buffer, how well it resists the change. So we'll just do 250 milliliters of H2O. No, not H2O. In this case, we're going to do the buffer, which is going to be 0.6309. So this is going to be 0.6309 molar base. The base was HPO42 minus, and 1.00 molar acid, H2PO4 minus. And this is going to create a pH 7.00 buffer. Okay, so we add 1 drop, and what we're going to end up with is 250.05 milliliters of solution. And so we'll calculate the new concentrations here. So the new concentration of HPO4 2 minus is going to be at 250. Oh, actually, yeah, 250 to 250.05 dilution of 0.6309 molar. It barely changed. And so this is a 250 divided by 250.05 times 6, or no, times 0.6309. 0.63077. And so we'll just go 0.6307 molar. So it barely changed, but it did change. And the new concentration of the acid component, H2PO4 minus, is a 250 over 250.05 dilution of 1.00 molar. And so 250 divided by 250.05 gives me 0.9998. 0.9998. I'm not going to round yet. Okay, the reason the pH doesn't change much in a buffer solution is not because of this. It's because of what the other species that we're adding to it. The other species we're adding to this is the strong acid. And so this is the crucial part. The strong acid is going to be a 0.05 to 250.05 dilution of 6 molar. And we just did that calculation. So the concentration of the HCl is going to be 0.001199. 0.001199 molar here. Okay, now what we do when we have a mixture like this is anytime we're given a complex mixture, we take the strongest acid plus the strongest base. So strongest acid plus strongest base. In this case, the strongest acid is going to be HCl. Will be the strongest acid. And the strongest base is going to be the monohydrogen phosphate, not the dihydrogen phosphate. This will be the strongest base. So the base is going to pluck the hydrogen off the acid. So what we're going to be left with is chloride plus dihydrogen phosphate. All right, then we're going to plug in our initials. The initial HCl after dilution is 0.001199. The initial concentration of monohydrogen phosphate is 0.6307. Chloride is 0. But we have the other product. The other product is dihydrogen phosphate. Dihydrogen phosphate is 0.9998 molar. Strong react to completion. So HCl here, K is going to be very, very large. And so we got to figure out what the limiting reagent is. The HCl is going to be the limiting reagent, and so we're going to be left with no HCl. So buffers are going to neutralize the acid, the added acid here, and we're going to lose some of the base. And so we're going to lose how much of the base? 0.001199. So I'm going to take 0.6307 minus 0.001199. And that gives me 0.6295. Where's my cursor? 0.6295. And then we're going to add the chloride. Does chloride do anything? No. Chloride's neutral, so we don't even pay any attention to that as far as pH goes. But I'll add it in there. And then we're going to convert some of the base component into acid component. So this is going to be plus 0.001199, which is going to give us what? So I'm going to take 0.9998 plus 0.001199. That gives me 1.0009. Okay, so what happens is the buffer's working. The base component neutralizes any added acid, and what happens? The ratio changes a little bit. So we went from 637 to 629.5, and we went from 0.9998 to 1.00. But did it change much? Doesn't look like it changed much. So let's calculate the new pH, because step 2, this is a buffer mixture. This is the base and its conjugate acid. That's an HH buffer. There's no more strong acid there. And so let's go ahead and calculate the new pH. The new pH is going to be, pH is equal to pKa, which was 7.200, plus the log of the base. The base is 0.6295. 6295. The acid is 1.0009, and this is going to come out to 0.6295 divided by 1.0009 equals, take the log of that, equals minus 0.201 plus 7.2. Let me 6.998. So the new pH comes out to 6.998. So the pH did drop, but barely. Do you see that? And in fact, if we were to round this to the correct number of sig figs, this just rounds to 7.00. And so we add a drop of HCl to unbuffered water. pH changed by 4 orders of magnitude and became 10,000 times more acidic. We add 1 drop of 6 molar HCl to a buffer, and the pH barely changed. Do you see that? And so this is the action of buffers, why buffers are important. All right, I'm going to stop here, and then we'll do the lab. But one thing about the lab is this. One of the steps, we're going to use solid sodium bismutate. Solid sodium bismutate is a brown powder. But the special chemical property of sodium bismutate is it's a strong oxidizer. It's one of the strongest oxidizers. It's not on our chart, but it's extremely powerful oxidizer. And what this powerful oxidizer does is it takes manganese ion, manganese 2+, and converts it into permanganate. So permanganate itself is a powerful oxidizer, so sodium bismutate must be more powerful than permanganate. So watch out, with that stuff. Don't inhale it. And in fact, I recommend doing it in the hood. Don't get it on your skin. Don't inhale it. Don't get it in your eyes. It'll cause significant oxidative damage if you do. So you just be very careful when you use it. Extra careful. You just need a little bit and you're going to form grape juice. You know, permanganate ions in water look like grape juice. And so you're looking to make purple grape juice. Okay. All right, any questions on that? We're going to continue this lab after spring break, so you don't have to finish today either. Take a look at your crystals and do a progress check on the crystals. We're going to have to probably take some action on the crystals.